Welcome. In this lecture we're going to talk about linear momentum, and we're going to look at the conditions under which it's conserved. So first we're going to define linear momentum, and we're going to start in a very familiar spot, and that would be Newton's second law. So with Newton's second law, we have the sum of the forces acting on a system of objects is equal to the mass of that system times the acceleration. Nothing new there. And we've started here before when we first looked at the work-energy theorem. Now we're going to take the acceleration and we're going to define it with our change in velocity over time. So if we change the acceleration to delta v over delta t, then we do a little bit of rearranging. Let's multiply both sides by delta t. So we have the sum of the forces acting on the system times t is equal to mass times delta v. And this should be a delta t, a time interval here. All right, now this mass times delta v over here, that is a special quantity, and that is called linear momentum. And writing it out explicitly here, we have m times v final minus m times v naught. And that's going to be the sum of the forces acting on the system times delta t. All right, so we're going to look at first this side of the equation, this mv final minus mv naught. And this, again, mass times velocity is defined as linear momentum. We will get to this force times delta t part in another lecture video, but for right now, let's focus on m times v. So linear momentum is given the variable or symbol lowercase p, and it is mathematically defined as an object's mass times its velocity. And we see that we're multiplying a scalar times a vector quantity. So that means that linear momentum is a vector quantity, and we have to treat it as such. So if we're going to add linear momentums up, we need to add them vectorially using triangles or using components. For right now, let's just say everything's moving in one dimension. And let's just take a look at something like, the units of linear momentum. Let's see, we have a mass, which is a kilogram, times the unit for velocity, which is meters per second. And that is the unit for momentum. It doesn't have anything special. A kilogram, meter per second. No special name for that. All right. Now let's go back and look at our original initial equation. We have the sum of the forces acting on the system times the time interval is equal to the change now in p. We're not going to do mv final minus mv naught. We'll call it the change in the linear momentum. And what we're going to find out here is the left-hand side of this is called the impulse, and the right-hand side is the change in momentum. Well, under very special circumstances, the left-hand side becomes 0. And that happens when the net force acting on the system is 0. So if the net force acting on the system is 0, then we get something very special happening. So if the net force on the system is 0, then we get 0 is equal to the change in momentum, which is p final minus p initial, which, simplifying, we have initial momentum is equal to the final momentum. All right, so this is called conservation of linear momentum. Conservation. And the condition that has to apply for linear momentum to be conserved is this one right here. The net force acting on the system is 0. And if that's the case, then we know linear momentum is conserved. What we're going to find out is that there are situations where linear momentum is conserved where energy is not. And that allows us to solve some problems in these types of situations really easily and very eloquently. So let's look at one of these types of problems, this whole class of problems that are generally called explosions. And they don't always deal with explosions. Let's look at a pretty simple example here. We have Bobby, who is in shape. His shape happens to be a rectangle. And we have Susie, who is also in shape. And these two are sitting on an ice skating rink. And it's very low friction, so low that we can ignore it. And Bobby here pushes on Susie with some force F. And we know from Newton's third law that Susie pushes back on Bobby with another force equal and opposite, F. So these two are pushing on one another. Now this force F is an internal force. If we talk about Bobby and Susie as the system as a whole, then the net internal force cancels here, the force that Bobby pushes on Susie with and Susie pushes on Bobby with, and we get no net external force acting. All right, so if F net is equal to 0, then momentum is conserved. And if P naught equals P final, we can solve for some problems involved in the system. So let's say that Bobby has a mass of big M and Susie has a mass of little m, and let's say that after they push off of one another, we measure Bobby's velocity, and he's going back to the left with some velocity VB. So the question we want to ask is, what is Susie's velocity, Vs, going off in the other direction? So net external force is 0, momentum is conserved, so we start at that position. The initial momentum of the system is equal to the final momentum of the system. And now, filling this out more specifically, we know that the total mass of the system times the initial velocity of the system is going to equal the total mass of the system times the final velocity of the system. And we can kind of simplify this by thinking of Bobby's initial momentum plus Susie's initial momentum is equal to Bobby's final momentum plus Susie's final momentum. So writing that out more fully, we have the mass of Susie times V naught of Susie plus the mass of Bobby times V naught of Bobby is equal to the mass of Susie times V final of Susie plus the mass of Bobby times V final of Bobby. All right, so things get really simple here. Bobby and Susie initially are at rest, so that makes the left-hand side of this equation very easy. It's 0. The initial momentum in the system is 0. And you think, hold on, wait a minute. Momentum is conserved. Bobby and Susie aren't moving initially. It's fine that the initial momentum is 0. Great. But after they push off of one another, both Bobby and Susie have momentum. So how can the momentum of the system still be 0? That comes from the fact, again, that momentum is a vector. So this is vector addition. Susie's moving to the right. She has positive momentum, positive being the direction of the momentum. Bobby's moving to the left. His momentum is negative. You add up Bobby's final momentum and Susie's final momentum, they should add to 0 if momentum is conserved. All right, so we have on the right-hand side of the equation, mass of Susie times V final of Susie plus mass of Bobby times V final of Bobby. And now remember again, we're looking for the final velocity of Susie. We know we measured Bobby's velocity. All right, so solving for V final of Susie, we have negative MB V final of Bobby divided by mass of Susie, and that gives us Susie's final velocity. All right, and notice here the negative that we have on the left-hand side. Well, Bobby's final velocity is negative, so we're going to plug in a negative there, and the negative from Bobby's final velocity is going to cancel out the negative that's in front of that equation, and we're going to get a final velocity of Susie being positive to the right. All right, that's lovely. That's great. And that works out. So explosions, generally the initial momentum of the system is 0, and that means the final momentum of the system has to be 0. That's one class of problems that we can solve. Notice also that we could have solved this with Newton's second law, F equals ma. If we know the force that Bobby pushes on Susie with, then we could find her acceleration. And if we know her acceleration, and we know we need to know something else. Well, her initial velocity is 0. Then we could find out what her final velocity would be using Newton's second law as well. Conservation of momentum, pretty quick and easy though. Okay, let's take a look at another class of problems that conservation of momentum allows us to solve, collisions. So here we have a cart of mass m moving to the right at 5 meters per second, and another cart of mass 2m at rest. These two carts are going to hit each other, and let's say that they have magnets, and they're going to attach to one another and stick together. So after the collision, we have m and we have 2m stuck together and moving off at some final velocity. All right, so is linear momentum conserved here? Let's see. M pushes to the right on 2m, speeding it up. 2m pushes back to the left on m. Again, Newton's third law. Conservation of linear momentum is really a different way of looking at Newton's third law. The forces are equal and opposite. That's an internal force to the system. It cancels out, so the net force acting is 0. Should also say no friction here, or small enough that we can ignore it. All right, so net external force is equal to 0. That means that P naught is equal to P final. Initial momentum of the system is equal to the final momentum of the system. So we think, who's got momentum initially? The m cart does. So we have m times 5, that's mass times velocity, and that is a positive 5 moving to the right, is going to equal, now they're stuck together, so we have m plus 2m is the total mass times v final. So solving for v final here, we have 5m is equal to 3m times v final. So 5m over 3m is equal to the final velocity of the system. The m's do cancel out here, and we get 5/3 meters per second is equal to v final. Does it make sense? Well, yeah, we know that m is going to slow down. We know that 2m is going to speed up, so it should be less than 5 and greater than 0 in this case. Okay, now one final thing to look at here is energy conserved in this collision? Remember that for energy to be conserved, we have to have only conservative forces acting on the system. So these two guys couple together and hang out. So is energy conserved? Let's see here. Does K naught equal K final? The initial kinetic energy is going to be 1/2 m times 5 squared. The final kinetic energy is going to be half the total mass now, 3m, times 5/3, and that whole thing squared. So on the left-hand side, we have 25/2 over times m. And on the right-hand side, we have, let's see, 25 times 3 is 75 sixths. Nope, I totally did that wrong. 25, and that's going to be 9 times 2, 18. 75 eighteenths m. So 25/2 m equal to 75 eighteenths m? Nope, not even close. So here we see that energy is not conserved. The final kinetic energy of the system is less than the initial kinetic energy of the system. And that's because there is work done in this coupling, in bringing these together and sticking them together. And that work takes kinetic energy out of the system, takes mechanical energy out of the system. This is a specific type of collision called an inelastic collision. And in these inelastic collisions, energy is not conserved. And that's how you can identify an elastic versus an inelastic collision. So there it is. In these two types of problems, explosions and collisions, we only have Newton's third law pairs acting between the objects. And in those cases, those internal forces cancel out. The net force on the system is 0. Momentum is conserved. And our starting point then is going to be that. Just remember, momentum is a vector. If it's going to the right, positive. Going to the left, negative. You have to add these guys vectorially. See you next time.